Look up at the night sky. For all of human history, those pinpricks of light have represented the ultimate frontier, distant and seemingly untouchable. We've dreamed of bridges to the stars, constructing them in our imaginations and our stories. But what if we've been looking at this the wrong way? What if the gateway to the cosmos isn't a structure we need to painstakingly engineer and launch into the void, but something far more mysterious and innate? What if it's a natural phenomenon, one that is quietly, invisibly forming around our planet at this very moment? This isn't science fiction. This is the cutting edge of space physics, a field where theory is beginning to catch up with the awe-inspiring potential of the universe itself. We are talking about the possibility of natural stargates, transient doorways woven from the very fabric of space-time, and the evidence suggests they might be flickering into existence right above our heads. Scientists call these theoretical phenomena X-point portals. They are not giant, shimmering rings like in the movies. Instead, they are points, elusive, temporary regions where the sun's magnetic field and Earth's own magnetic shield, the magnetosphere, interact in a violent and beautiful dance. At these precise locations, a process known as magnetic reconnection occurs. Think of it like two cosmic rivers of magnetic force crashing into one another, breaking, and then reforming in a new configuration. In that moment of reconnection, something extraordinary may happen. The laws of physics as we understand them might allow for a shortcut, a tunnel through the tangled geometry of space and time itself. It's a concept that pushes the boundaries of our understanding, suggesting that the universe might be filled with these hidden passageways, and that Earth is sitting at the center of a celestial crossroads. So the question is no longer just about how we can get to the stars, but what it means that the stars might have a way to come to us. In this video, we will embark on a journey to explore the compelling science behind X-point portals. We will delve into the data from spacecraft that have potentially flown right through them, unpack the theories that make them possible, and confront the profound implications. If these natural stargates are real, they could rewrite the future of exploration, challenge our place in the cosmos, and reveal a universe that is far more interconnected and wondrous than we ever dared to dream. This is a story of discovery, of cosmic clues hidden in plain sight, and of the possibility that the greatest adventure lies not in the distant heavens, but in the invisible fields that embrace our world. To understand how such a cosmic shortcut could exist, we need to start with the invisible forces that constantly envelop our planet. Earth is cocooned within a protective bubble called the magnetosphere, a region dominated by our planet's own magnetic field. Streaming toward us from the sun is the solar wind, a constant supersonic flow of charged particles that carries with it the sun's magnetic field. Most of the time, our magnetosphere acts like a shield, deflecting this solar onslaught. But this boundary is not a perfect, impenetrable wall. It's a dynamic and turbulent frontier where these two powerful magnetic fields meet, push, pull, and sometimes dramatically merge. This merger is the key event, a process physicists call magnetic reconnection. The best way to visualize this is not with complex equations, but by thinking about two incredibly powerful, twisted rubber bands. Imagine you have one rubber band representing the sun's magnetic field and another representing Earth's. They are pressing against each other, storing up energy like a spring being compressed. As the pressure builds, the fields can no longer hold their separate shapes. They snap, breaking at a specific point, and then instantly reconnect in a new configuration. But instead of rubber bands, we're talking about the fundamental architecture of space-time itself being twisted and re-knitted. In that moment of snapping and reconnection, the stored magnetic energy is unleashed in a violent burst, accelerating particles to nearly the speed of light and theoretically warping the local geometry of space. The precise spot where this celestial snapping occurs is known as the X-point. It gets its name from the distinct cross-shaped pattern the magnetic fields form at that location. It's not a physical object you could touch. It's more like a fleeting event, a chaotic intersection in the magnetic highway. This X point is the heart of the potential portal. The reconnection process is so extreme that it might briefly create a region where the normal rules of physics are bent, allowing for a direct connection, a shortcut between two vastly distant points. Think of it like a short circuit in a massive electrical grid. For a split second, the current finds a new, unexpected path, bypassing the normal resistance. An X-point portal could be a short circuit in the cosmic magnetic grid, creating a temporary bridge through what would otherwise be an impassable void. Crucially, this is not just theoretical speculation. While the idea of these portals serving as stargates is a breathtaking extension of the science, the underlying process of magnetic reconnection is a confirmed and actively studied phenomenon. NASA's Magnetospheric Multiscale Mission, or MMS, is a fleet of 4 identical spacecraft flying in a tight formation specifically designed to study these events. They have flown directly through X points in Earth's magnetosphere, collecting data with unprecedented detail. They've observed the explosive energy release, the particle acceleration, and the fundamental physics of the reconnection process itself. So we know for a fact that these cosmic snap and reconnect events are happening. The open question, the thrilling frontier of research, is what else is happening in those fleeting moments? Are we merely witnessing a powerful energy transfer, or are we catching a glimpse of something far more profound, a natural doorway written into the laws of the universe itself? And it is this direct evidence that truly transforms the concept from a fascinating theory into a tangible reality. The Magnetospheric Multiscale Mission, often called MMS, represents one of the most sophisticated scientific detective operations ever conceived. Launched in 2015, its sole purpose is to act as a cosmic-scale microscope, focused intently on the elusive X points. What makes this mission so revolutionary is its formation. The 4 identical spacecraft don't just fly near each other. They maintain an incredibly precise, tight pyramid formation, sometimes separated by distances as small as 10 kilometers. To put that in perspective, at their orbital altitude, that's like 4 synchronized hummingbirds flying in perfect formation across an entire continent. This coordinated flight is the key. It allows the fleet to do something no single satellite could ever achieve: capture a 3-dimensional, high-definition movie of a magnetic reconnection event as it happens. As these spacecraft sweep through the boundary between Earth's magnetic field and the solar wind, they are equipped with sensors so sensitive they can measure particle movements fractions of a second apart. When they encounter an X point, they don't just see a blur of energy, they map it. Each satellite records the direction, speed, and density of charged particles from its unique vantage point within the pyramid. By combining this data, scientists can reconstruct the entire structure of the portal in stunning detail, observing how magnetic field lines break, snap, and reconnect in a violent, orchestrated dance. The findings have been nothing short of breathtaking. These portals are not small. They can span tens of thousands of kilometers, large enough to swallow the entire Earth with room to spare. Yet for all their immense size, they are astonishingly ephemeral. They flicker into existence, often for just a minute or even less, before dissolving back into the invisible magnetic sea. It's a cosmic version of a soap bubble, vast, complex, and beautiful, but vanishing in the blink of an eye. Perhaps the most staggering data concerns the sheer violence occurring within these brief windows. The MMS mission has clocked electrons being accelerated to speeds that defy comprehension, hurtling along the reconnected magnetic field lines at nearly the speed of light. These are not gentle currents, they are explosive jets of raw energy. Imagine the power of 1,000,000 thunderstorms focused into a single, narrow beam. This isn't passive energy either. It's a dynamic process where the magnetic energy is directly converted into particle motion and heat, a fundamental engine that drives space weather around our planet. The mission has confirmed that these events are not rare celestial oddities. They are a regular and fundamental part of the Sun-Earth relationship, occurring multiple times each day. This constant, hidden activity paints a picture of our near-Earth environment not as a quiet void, but as a seething, dynamic arena where magnetic portals are constantly opening and closing, churning the very space around us. Now, with all this incredible data confirming the existence of these vast, energetic portals, it's easy for the mind to leap to the iconic imagery of science fiction. The giant, stable rings that hum with energy, creating a calm, walkable doorway to another world. It's a thrilling comparison, but it's also essential to draw a clear line between the cinematic fantasy and the complex reality. The X-point portals discovered by science are not those polished, user-friendly Stargates. In fact, they are almost the complete opposite in nearly every way that matters for travel. The most fundamental difference lies in their stability. A sci-fi Stargate is a marvel of engineering designed to open a persistent, controlled corridor. It's built to last, a permanent fixture. A natural X-point portal, however, is a cosmic ephemeron. It's a temporary rupture in the magnetic fabric of space, flickering into and out of existence in a matter of minutes, sometimes even seconds. Trying to navigate one would be like trying to ride a lightning bolt. The pathway simply vanishes before you could even begin the journey. There is no stability, no predictability. It's a burst of energy, not a constructed tunnel. Then there's the environment within the portal itself. Picture the serene, shimmering pool of light within a movie Stargate. Now replace that image with the heart of the sun. An X-point portal is not an empty void. It is a maelstrom of searing plasma, a superheated gas of charged particles. Electrons and protons are being whipped to relativistic speeds, creating a destructive environment of intense radiation and unimaginable heat. Any physical object, whether a sophisticated spacecraft or a simple probe, would be instantly vaporized by the torrent of energy. This isn't a hallway, it's the core of a magnetic explosion. This leads to the most critical distinction, traversability. The wormholes often depicted in fiction are what physicists call traversable wormholes. They are theoretical solutions to the equations of general relativity that could, in principle, allow something to pass from one end to the other unscathed. The natural portals formed at magnetic X-points are almost certainly not traversable in this sense. They are believed to be incredibly short-lived structures that may connect magnetic fields over short distances in space, but they do not offer a safe, coherent pathway for matter. They are a manifestation of energy transfer, not a designed transportation system. So, while the term Stargate captures the imagination and the fundamental idea of a connection, the reality is far wilder, more destructive, and in its own way more fascinating. It's a force of nature, not a tool. Given their fleeting and violent nature, you might assume these X-point portals are rare celestial events, but the truth is far more astonishing. According to data from missions like MMS, these portals are not rare at all. They are a regular part of Earth's cosmic weather, opening and closing dozens of times each single day. If you were to somehow stand on the surface of our planet and look up, you wouldn't see them, but above you, in the invisible magnetic realm, a doorway is likely flickering into existence right now. This constant hidden activity reveals that our planet is not sitting in a quiet pool of space, but is rather at the center of a dynamic, churning intersection of cosmic forces. So where exactly are these daily events happening? Their formation follows a distinct and predictable pattern tied directly to the sun's relentless pressure. The most active site is the day side of Earth's magnetosphere. This is the front line, the region facing directly into the oncoming solar wind. Here, the sun's magnetic field presses incessantly against our planet's magnetic shield. As this pressure builds, it stretches Earth's magnetic field lines back away from the Sun like streamers in a strong wind. It's at this boundary where the two fields are pressed tightly together that magnetic reconnection is most likely to be triggered. A sudden surge in solar wind pressure can be the final straw, causing the fields to snap and a portal to briefly flare into existence. Visualize it as a cosmic version of ocean waves constantly crashing against a rocky cliff, with each powerful impact sending spray into the air. Only here, the spray is a temporary gateway. But the activity doesn't stop there. On the opposite side of Earth, stretching far out into the darkness away from the Sun, lies the magnetotail. This is the long, trailing portion of our magnetosphere, pulled and stretched by the solar wind into a shape resembling the tail of a comet. While the day side is about direct confrontation, the magnetotail is about storage and release. The solar wind's energy is deposited here, building up tension in the magnetic field lines. Much like a rubber band that's been stretched too far, these field lines in the tail can suddenly snap back toward Earth in a massive reconnection event. These nightside portals are often even more energetic than their dayside counterparts, and they play a critical role in driving the spectacular auroras that dance over our poles, funneling vast amounts of solar particles into our upper atmosphere. The challenge for scientists, then, is not necessarily finding evidence that portals exist, but catching them in the act. Their unpredictability is the great obstacle. While we know they form dozens of times a day, pinpointing the exact moment and location of a specific portal is incredibly difficult. They are transient phenomena, appearing without warning and vanishing just as quickly. This is where statistical modeling becomes a powerful tool. By analyzing years of data from satellites, researchers can identify the specific conditions that favor portal formation, certain solar wind speeds, particular orientations of the Sun's magnetic field, and levels of geomagnetic activity. These models don't predict a single event with certainty, but they can highlight periods of high probability, giving missions like MMS a much better chance of being in the right place at the right time to witness the birth and death of these natural stargates. So what is this invisible river of energy that has such power to warp the very space around our world? To understand the engine of these portals, we need to turn our gaze directly to the Sun. Our star is not a quiet, static ball of light. It is a dynamic, churning sphere of plasma, and it is constantly exhaling a breath of charged particles out into the solar system. This exhalation is the solar wind, a supersonic stream that flows past Earth at speeds ranging from 1 to 3 million miles per hour. But the solar wind is far more than just a stream of particles. It's a carrier, a delivery system for the Sun's own magnetic personality. This is where the concept becomes truly fascinating. Woven into this fast-moving plasma is the Sun's magnetic field, which stretches out across the entire solar system. Scientists call this the interplanetary magnetic field, or IMF for short. Think of it not as a simple bar magnet, but as a complex, wrinkled tapestry that is carried along by the solar wind, like a pattern woven into a flowing river. As this magnetized wind travels the 93 million miles to Earth, it brings the Sun's magnetic influence right to our doorstep. When this solar wind, with its embedded IMF, finally reaches Earth, it encounters our planet's own strong, global magnetic field, our magnetosphere. This sets the stage for an epic, invisible confrontation. Most of the time, our magnetosphere does an excellent job deflecting the solar wind, shaping it around our planet like a rock diverting the flow of a stream. But the nature of that interaction changes dramatically depending on a single, critical factor: the direction the Sun's magnetic field is pointing when it arrives. Here lies the key to unlocking the portal. Earth's magnetic field is oriented roughly north-south, emerging from the southern hemisphere and entering in the northern hemisphere. Now imagine the Sun's magnetic field, the IMF, also has a direction. when the IMF is pointing northward in the same general direction as Earth's field at the boundary where they meet, the two fields are said to be aligned. In this configuration, they behave like two magnets with the same pole facing each other. They repel. The solar wind slides more smoothly around the magnetosphere, and things remain relatively calm. However, when the IMF flips and points southward, the conditions become perfect for a cosmic storm. A southward-pointing IMF is directly opposite to Earth's northward-oriented field at the dayside boundary. Instead of repelling, these opposite magnetic orientations are primed to connect. It's like two magnets with opposite poles snapping together, but on a planetary scale. This southward orientation is the trigger. It allows the Sun's magnetic field to merge directly with Earth's in the process of magnetic reconnection we discussed earlier. The opposing field lines are driven together by the pressure of the solar wind. They cross, break, and reconnect. In that explosive moment, the magnetic topology is rewritten and an X-point portal is born. The solar wind is no longer just flowing around. Its energy is now being funneled directly into the heart of our planet's magnetic shield, opening a temporary gateway. This is why space weather forecasters pay such close attention to the direction of the IMF. A prolonged period of southward-pointing magnetic field from the Sun is a sure sign that energy is about to be transferred on a massive scale, potentially sparking not just the formation of portals, but also triggering intense geomagnetic storms and brilliant auroral displays. The solar wind, therefore, is much more than a steady breeze. It is a variable and powerful sculptor whose magnetic brushstrokes paint dynamic, temporary doorways across the sky. This constant opening and closing of portals is far from a passive celestial light show. In reality, these fleeting events are the primary engines of space weather, acting as cosmic gatekeepers that control the flow of energy into our planet's protective bubble. When a portal opens, even for just a minute, it creates a direct pipeline. Through this pipeline, the solar wind, that relentless stream of energy, mass, and momentum from the Sun, floods directly into regions of space that are normally shielded. It's the difference between a gentle rain and a fire hose being turned on a single spot. The magnetosphere, which usually deflects most of this onslaught, suddenly has a breach, and the results are both beautiful and potentially devastating. The most immediate and visible consequence of this energy transfer is the aurora. The breathtaking northern and southern lights are not simply a colorful curtain painted onto the sky. They are a direct symptom of energy pouring through these X-point portals. Here's how it works. When magnetic reconnection occurs on the night side of Earth in the magnetotail, it acts like a cosmic slingshot. The process accelerates vast waves of electrons down magnetic field lines that are now connected directly to the polar regions. These high-energy particles race toward Earth, following the planet's magnetic field down to the poles. When they collide with atoms and molecules in the upper atmosphere, primarily oxygen and nitrogen, they transfer their energy, causing those atoms to light up in the signature greens, reds, and purples of the aurora. So, every time you witness that shimmering display, you are essentially watching the aftermath of a natural stargate flickering open hundreds of thousands of kilometers away, funneling the Sun's power to our doorstep in a radiant cascade. But the influence of these portals extends far beyond creating beautiful lights. Under more extreme conditions, this energy transfer can escalate into a full-blown geomagnetic storm. Imagine the Sun unleashing a particularly powerful event, like a coronal mass ejection, a billion-ton cloud of magnetized plasma hurled toward Earth at millions of miles per hour. When such a cloud arrives, it can force the magnetosphere to undergo massive, global reconfiguration. X-point portals may form not as isolated events, but in rapid succession across a vast area, opening multiple floodgates simultaneously. The influx of energy becomes overwhelming, causing the entire magnetosphere to vibrate and shake like a bell that has been struck. This is when the technological hazards emerge. The violent fluctuations in Earth's magnetic field during a geomagnetic storm induce powerful electrical currents in the ground itself. These currents can seek the path of least resistance, which often means flowing through our man-made infrastructure. Long-distance power lines and oil and gas pipelines can act as giant antennas for this energy, overloading transformers and potentially causing widespread, long-lasting blackouts. Satellite operations are severely threatened. The increased radiation can fry sensitive electronics, alter their orbits through increased atmospheric drag, and disrupt GPS and communication signals that our modern world relies upon. The famous Carrington event of 1859, which caused telegraph systems to fail and sparks to fly from equipment, was a historic example of what a severe geomagnetic storm can do. A storm of that magnitude today would have catastrophic consequences for our technology-dependent society. This is precisely why understanding the physics of X-point portals transcends abstract scientific curiosity. It is a matter of practical, global security. By learning to predict when and where these portals will form based on solar wind conditions, we move closer to creating reliable space weather forecasts. Just as meteorologists track hurricanes to give coastal communities time to prepare, space physicists aim to predict the severity of an incoming solar storm. Accurate forecasting would allow satellite operators to put their assets into safe mode, power grid managers to implement protective measures, and airlines to reroute flights away from high-radiation polar routes. The study of these mysterious portals is therefore a critical step in building societal resilience against the natural rhythms of our star, transforming a cosmic phenomenon from a potential threat into a predictable force of nature that we can learn to navigate. And so, the seemingly abstract dance of magnetic fields reveals its most breathtaking signature in the night sky, the aurora. This celestial ballet of light is not a random decoration. It is the direct, visible evidence of energy traveling through those very X-point portals we've been exploring. The journey begins far out in space at a portal that has momentarily opened, often on the night side of Earth in the magnetotail. When magnetic reconnection occurs there, it acts as a powerful particle accelerator. Electrons caught in the magnetic turmoil are suddenly hurled at incredible speeds down the newly reconnected magnetic field lines. These lines act like cosmic highways, and they all converge at the polar regions of our planet. So imagine these energized particles shot like bullets from a cosmic gun, following these invisible tracks that guide them directly toward the north and south poles. As these high-speed electrons dive into our upper atmosphere, they begin to collide with the thin soup of gas molecules, primarily oxygen and nitrogen, that resides there about 100 kilometers above the ground. These collisions are not gentle bumps, they are violent transfers of energy. An electron smashes into an oxygen atom, for instance, and in that instant, it gives some of its energy to the atom's electrons, pushing them into a higher, excited state. But nature seeks balance. Almost immediately, those excited electrons release their extra energy to return to their normal state, and they do so by emitting a photon, a particle of light. The specific color of that light depends entirely on which gas is being struck and at what altitude. Collisions with oxygen at higher altitudes produce rare, deep red auroras, while oxygen at lower altitudes creates the familiar, brilliant green. Nitrogen, on the other hand, contributes stunning hues of blue and purple. What we perceive from the ground as gently waving curtains of color is actually the collective glow of trillions upon trillions of these individual atomic collisions, a luminescent fallout from a magnetic explosion that occurred hundreds of thousands of kilometers away. This direct link transforms the aurora from a beautiful mystery into a powerful scientific tool. By carefully studying the intensity, movement, and colors of an auroral display, researchers can actually work backwards to understand the conditions at the portal that created it. A particularly dynamic and fast-moving aurora, for instance, suggests a more violent and energetic reconnection event. The altitude and extent of the glow provide clues about the quantity and speed of the particles that were funneled down. This is where the predictive power comes in. Scientists using data from satellites like Themis and MMS can now model the reconnection process with increasing accuracy. By monitoring the solar wind and the orientation of the interplanetary magnetic field, they can forecast not just if an aurora will occur, but how intense it might be and precisely where the auroral oval, the ring of light around the poles, will be most active. Enthusiasts who chase the northern lights now rely on these space weather forecasts, which are fundamentally forecasts of portal activity, to know when to look up. The aurora, therefore, is more than a light show. It is a real-time diagnostic display, painting the story of invisible magnetic forces onto the canvas of our atmosphere, making the complex physics of X-point portals tangibly, beautifully clear for all to see. To truly appreciate the significance of what we're discovering today, we have to journey back to a time when the very idea of space having weather was considered radical. The story begins not with satellites, but with a determined Norwegian scientist named Christian Birkeland. In the late 19th and early 20th centuries, while others saw the ethereal glow of the northern lights as a mysterious atmospheric curiosity, Birkeland saw a clue. He was convinced the aurora was caused by electrically charged particles from the sun, an idea that flew in the face of the scientific consensus of his day. To prove his theory, he undertook daring expeditions into the Arctic cold, building observatories to meticulously map the auroral activity. He even created a miniature version of Earth, which he called a tarella, inside a vacuum chamber. By bombarding this small magnetized sphere with electrons, he successfully produced a tiny, glowing aurora around its poles. Birkeland had uncovered the fundamental link between the Sun and Earth's atmosphere, proposing that invisible electric currents, which we now call Birkeland currents, flowed along the planet's magnetic field lines. His work was the foundation, the first bold assertion that our planet is connected to the Sun by invisible, energetic pathways. For decades, Birkeland's theories were largely dismissed or overlooked. The mid-20th century, however, with the dawn of the space age, brought the tools needed to test his visionary ideas. The first primitive satellites, like the Soviet Union's Sputnik and America's Explorer 1, began venturing beyond the atmosphere. They carried instruments that could directly sample the space environment, and what they found was a revelation. They confirmed the existence of the solar wind, a constant stream of particles flowing from the Sun, just as Birkeland had inferred. They mapped the boundaries of Earth's magnetosphere, discovering it was not a static bubble but a dynamic structure constantly being shaped by solar activity. These early in situ measurements transformed space physics from a theoretical exercise into a hard science. We were no longer just observing from a distance. We were dipping our toes into the cosmic ocean, confirming that the space around Earth was filled with complex, interacting fields and particles. The stage was set for a deeper investigation into exactly how the Sun's energy breached our planet's magnetic defenses. The pivotal breakthrough came in the late 1970s. Scientists analyzing data from satellites noticed something peculiar: brief, sudden bursts of energy and magnetic field disturbances at the edge of the magnetosphere. These events didn't last long, but they were powerful and seemed to indicate a direct, temporary connection between the solar wind and Earth's magnetic field. In 1979, researchers C.J. Faris and S.W.H. Cowley gave these phenomena a name that would stick: the flux transfer event. This term was a game changer. It moved the discussion from vague ideas of connection to a specific, measurable phenomenon. A flux transfer event was essentially the signature of a magnetic portal opening and closing. It described the brief instant when magnetic field lines from the Sun and Earth linked up, allowing a burst of solar wind plasma to surge through. The name itself captured the essence, flux referring to the magnetic flow, and event highlighting its temporary nature. This conceptual leap allowed scientists to start searching for these events systematically, turning random anomalies into a class of object to be studied. With the concept of flux transfer events firmly established, the next step was to visualize the invisible. This is where computer simulations became an indispensable tool. In the 1980s and 90s, as computing power grew, physicists began creating sophisticated numerical models of the Sun-Earth interaction. They could program in the known laws of plasma physics and magnetic fields, and then watch what happened when a southward-pointing solar magnetic field pressed against Earth's magnetosphere. The results of these simulations were stunning. The models consistently predicted that the magnetic reconnection would occur at a specific, precise location, a point where the fields formed a distinct X-shaped pattern. This was the theoretical X-point brought to life on computer screens. The simulations showed the field lines breaking and reconnecting at this nexus, creating a temporary opening. For the first time, scientists had a geometrical model for the portal. It wasn't just an event, it had a structure. This marriage of satellite data and computer modeling bridged theory and observation, creating a robust framework that pointed directly to the existence of X-point portals as the physical mechanism behind the flux transfer events. It was this convergence of historical insight, direct measurement, and theoretical modeling that paved the way for missions like MMS, equipping us with the knowledge to finally go out and capture these natural stargates in action. Capturing these fleeting portals is one of the most daunting challenges in modern space physics. The primary obstacle is their sheer unpredictability and brief existence. While we know these events are happening dozens of times a day, each individual portal is like a lightning strike in a global thunderstorm, immensely powerful, but appearing and vanishing in an instant within an unimaginably vast arena. The region where they form, the magnetospheric boundary, is an enormous volume of space. A scientist can't simply point a telescope and wait. They have to have a sophisticated spacecraft in exactly the right place, at exactly the right millisecond, with its instruments perfectly configured. It is the ultimate cosmic needle in a haystack search, where the haystack is the size of a planet and the needle only materializes for a minute or less. For decades, our ability to study these events was severely hampered by the limitations of single spacecraft missions. A lone satellite passing through the magnetosphere is akin to a single weather buoy in the middle of the ocean. It can tell you what the conditions are like at its specific location at one moment: the temperature, the wave height, the wind speed. But it cannot tell you if a hurricane is forming 50 miles away, nor can it show you the structure of that storm as it develops and moves. When a single satellite detected a burst of energy or a shift in the magnetic field, it was like hearing a single, isolated note from a symphony. Scientists could infer that something significant had happened, but they were left guessing at the larger melody. Was it a small, localized event or part of a massive, coordinated phenomenon? How did it start? How did it evolve? A single point of measurement simply cannot answer these questions. It provides a puzzle piece, but not the picture on the box. This fundamental limitation is what made the multi-satellite approach of the magnetospheric multiscale mission such a revolutionary leap forward. Instead of one weather buoy, MMS deployed 4. Flying in an incredibly precise tetrahedral formation, these 4 identical spacecraft act as a single, coordinated observatory. Their power lies in their ability to make measurements simultaneously from 4 slightly different points in space. This allows scientists to move from simply detecting an event to actually visualizing its structure and dynamics in 3 dimensions. Imagine trying to understand the shape and force of a waterfall by dipping a single cup into the river below. You'd get wet, but you wouldn't comprehend the cascade. Now, imagine placing 4 cups at different points across the waterfall's edge. By comparing how much water enters each cup and at what time, you could start to map the flow's intensity, its changing patterns, and its overall form. That is the transformative capability MMS brought to the study of X points. However, collecting the data is only half the battle. The other monumental challenge lies in the interpretation. The environment around these portals is not a clean, quiet vacuum. It is a turbulent sea of plasma filled with a cacophony of waves, currents, and particle flows. The signature of magnetic reconnection is just one signal buried within this roaring ocean of noise. Isolating it requires sifting through terabytes of information, searching for the specific telltale patterns that indicate field lines are breaking and reconnecting. Scientists look for sudden reversals in the magnetic field direction, jets of particles being accelerated to outrageous speeds, and specific alignments of electric and magnetic fields that only occur during reconnection. This is a task that demands immense computational power and sophisticated algorithms, a delicate process of digital archaeology to uncover the hidden story within the data. It is a testament to human ingenuity that we can not only send probes to these invisible frontiers, but also develop the methods to decipher the complex language of the magnetic universe they record. The immense challenge of observing these fleeting portals in the vastness of space is why scientists have turned to the digital realm, creating virtual universes inside powerful supercomputers. These theoretical models and simulations are not just helpful tools, they are absolutely essential, acting as a cosmic laboratory where we can run experiments that would be impossible in the real world. At the heart of this digital effort are two primary types of models, each offering a different lens through which to view the chaotic dance of magnetic reconnection. The first is called magnetohydrodynamics, or MHD for short. This approach treats the seething plasma of the solar wind and magnetosphere as a single, fluid-like substance. Imagine trying to predict the weather in a hurricane by tracking the overall movement of the storm system, the swirling clouds, the drop in pressure, the wind patterns. An MHD simulation does something similar for space weather. It models how the large-scale magnetic fields and the plasma bulk flow interact, giving scientists a big-picture view of how energy propagates and where conditions become ripe for portals to form. These simulations are brilliant at showing the global context, revealing how a disturbance on the sun side of Earth can trigger a chain reaction that echoes throughout the entire magnetosphere, much like watching ripples spread across a pond. However, to truly understand the heart of the explosion, the X-point itself, we need a microscope, not a wide-angle lens. This is where kinetic simulations come into play. While MHD treats plasma as a fluid, kinetic models dive down to the level of individual particles. They track the behavior of countless electrons and ions, simulating their complex motions and collisions within the magnetic and electric fields. This is a computationally monumental task, but it's the only way to capture the fine-scale physics that MHD approximations must gloss over. It's the difference between forecasting that a hurricane will make landfall and using a high-speed camera to study the intricate dynamics of a single raindrop within the storm. Kinetic simulations allow researchers to peer directly into the explosive engine of magnetic reconnection, observing how the magnetic field lines actually break and reconnect, and how particles are catapulted to nearly the speed of light in the process. The most sophisticated models today often combine these approaches, using a global MHD framework to set the stage, and then zooming in with a kinetic model to study the critical reconnection region in exquisite detail. The visualizations that emerge from these supercomputer runs are nothing short of breathtaking. They transform abstract equations into dynamic, flowing animations that vividly illustrate the birth of an X-point portal. You can watch as the solar wind presses against Earth's magnetic field, stretching it back. The field lines, represented as glowing strands of light, are forced together until at a critical point they cross. The simulation shows them pinching, then snapping violently, reforming in that distinct cross-shaped pattern that gives the X-point its name. From this nexus, you see jets of plasma superheated, charged gas exploding outward in opposite directions, a visual confirmation of the explosive energy release that satellites like MMS have measured. These aren't just pretty pictures, they are quantitative predictions. The simulations spit out specific numbers, how fast the particles will be accelerated, how much energy will be released, and how long the portal might remain open. These predictions become a crucial checklist for experimentalists. This creates a powerful, self-improving feedback loop that drives the entire field forward. A team running a simulation might predict, for example, that under a specific set of solar wind conditions, a portal will form at a certain location and inject a particular amount of energy into Earth's radiation belts. They then share this prediction with the scientists operating the MMS spacecraft or other satellites. Those mission planners can then attempt to position their spacecraft to fly through that predicted region, hunting for the telltale signatures. When the satellite data comes back, it is compared directly against the simulation's predictions. If they match, it's a major victory, providing strong evidence that our theoretical understanding is correct. But perhaps even more valuable are the times when the data and the model disagree. A discrepancy is not a failure, it's a discovery. It means there's a piece of physics missing from our equations, some complex interaction or unstable wave that we haven't yet accounted for. The model is then refined, the code is tweaked, and a new, better simulation is run. This continuous cycle of prediction, observation, and refinement is how we slowly, painstakingly, unravel the secrets of these natural stargates, using the digital universe to illuminate the hidden workings of the real one. This extraordinary environment within an X-point portal, a maelstrom of breaking and reconnecting magnetic fields, does far more than just create a temporary gateway. It acts as one of the most powerful natural particle accelerators in our solar system. The process is a testament to the raw energy involved in magnetic reconnection. As the magnetic field lines snap and reform, they release a tremendous amount of stored energy, much of which is channeled directly into accelerating any charged particles caught in the turmoil. Electrons and ions are not simply drifting through this space, they are violently hurled along the newly reconnected magnetic field lines. The forces at work are so immense that these particles can be boosted to relativistic speeds, meaning a significant fraction of the speed of light. In a region spanning thousands of kilometers, particles can be shot from one end to the other in a fraction of a second, gaining energies that would be impossible under normal solar wind conditions. It is a fascinating exercise to compare this cosmic accelerator to our most advanced human-made version, the Large Hadron Collider. Both achieve the same fundamental goal, accelerating subatomic particles to extreme velocities to study the fundamental laws of physics. Yet, the methods and the scales involved could not be more different. The LHC is a masterpiece of precision engineering, a 27-kilometer-long underground ring where superconducting magnets guide protons in a near-perfect vacuum. Its operation is meticulously controlled, with physicists carefully tuning every parameter to create specific, repeatable collision events. In stark contrast, the particle accelerator within an X-point portal is a product of pure, chaotic nature. It has no designed structure, no vacuum chamber, and no control panel. It is a transient explosion of magnetic energy that works on a scale far larger than any machine we could ever build, accelerating particles not in a neat circle, but along vast, open magnetic pathways that stretch across space. While the LHC allows us to probe the secrets of the quantum world in a lab, these natural accelerators are performing experiments on a galactic scale, demonstrating the fundamental processes that shape our universe. The implications of this natural acceleration are profound, particularly for a long-standing mystery in astrophysics, the origin of cosmic rays. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, that constantly bombard Earth from all directions in space. For over a century, scientists have been trying to pinpoint the cosmic engines capable of producing these particles, some of which carry energies millions of times greater than those achieved in the LHC. While the most energetic cosmic rays likely come from cataclysmic events like supernova explosions or active galactic nuclei, the X-point portals around Earth provide a nearby, observable example of a fundamental acceleration mechanism that is likely at work throughout the cosmos. They demonstrate that magnetic reconnection, a process that can occur anywhere you have turbulent magnetic fields from the surface of the Sun to the distant boundaries of nebulae, is a potent and universal way to energize particles. By studying the specific fingerprint of particles accelerated in our own backyard, scientists can develop models to identify similar processes occurring in far more extreme and distant environments, helping to solve the puzzle of where these intergalactic travelers get their incredible speed. Ultimately, the study of particle acceleration at X-points transcends this single mystery. It reveals a universe that is fundamentally dynamic and energetic. The serene emptiness of space, as seen from our planet, is an illusion. In reality, the cosmos is filled with invisible magnetic architectures that are constantly storing, releasing, and converting energy. The violent processes within these fleeting portals are not rare anomalies. They are a basic function of how magnetized plasma behaves. This means that wherever we find magnetic fields in conflict around other planets, near other stars, in the vast spaces between galaxies, we are likely to find natural particle accelerators at work. Understanding the mechanics of the X-point portal, therefore, gives us a key to understanding one of the universe's primary methods of transferring energy, a process that shapes the environments of planets, influences the evolution of stellar systems, and contributes to the high-energy radiation that fills the void. It shows us that the universe is not a quiet, static place, but a vibrant and ever-changing arena where the most fundamental forces are continuously at play. So we arrive at the most tantalizing question of all, the one that has fueled science fiction for generations. Could these natural X-point portals ever be used as gateways, as actual stargates we could travel through? To answer this, we must temporarily set aside the awe and venture into the rigorous and often unforgiving realm of theoretical physics. The idea of a traversable wormhole, a stable tunnel through space-time, is not strictly forbidden by Einstein's theory of general relativity. In fact, the equations allow for such structures, known as Einstein-Rosen bridges or Morris-Thorne wormholes. But allowing for, in a mathematical sense, is a far cry from being physically possible. The catch, and it's a monumental one, is that keeping such a wormhole open and safe for passage would require a form of matter with negative energy density, often called exotic matter. This isn't just a rare substance, it's something that, according to our current understanding, defies the fundamental energy conditions of the universe. It would need to have a repulsive gravitational effect, propping the throat of the wormhole open against its natural tendency to collapse instantaneously into a singularity. The energy requirements to create and sustain even a microscopic traversable wormhole are beyond colossal. They are truly astronomical, perhaps requiring the manipulation of mass energy on a scale comparable to entire stars. Now, let's place these theoretical requirements side by side with the observed reality of an X-point portal. The contrast couldn't be more stark. The portals forming around Earth are not serene, empty tunnels. They are the epicenter of a violent magnetic explosion. They are composed of seething, superheated plasma, a state of matter where electrons are ripped from their atoms, creating a destructive soup of charged particles. Within this maelstrom, radiation levels are intense enough to fry any known electronics and would be instantly lethal to any living organism. Furthermore, their defining characteristic is their profound instability. They are transient events, flickering into existence for mere minutes before the magnetic fields reconfigure and the portal vanishes. A traversable wormhole, as theorized, would need to be exquisitely stable for a duration long enough to allow something to pass through without being caught in a catastrophic collapse. An X-point portal is the polar opposite of this. It is a brief, chaotic burst, not an engineered, stable structure. This fundamental mismatch means that, with our present knowledge of physics, the answer is a definitive no. Attempting to pass a spacecraft, or even a simple probe, through a natural X-point portal would be akin to trying to sail a paper boat through the heart of a thermonuclear explosion. The vessel would be vaporized by the intense radiation and plasma long before any hypothetical shortcut could be utilized. The portal's nature as a region of energy transfer, not a coherent space-time tunnel, makes it inherently hostile to matter. It functions as a cosmic particle accelerator, not a celestial hallway. However, to close the door completely on the idea would be to ignore the dynamic nature of science itself. Our understanding of the universe is not a static picture but an ever-evolving narrative. While today's physics paints a clear picture of impossibility, history is filled with concepts once deemed unthinkable that later became reality. The discovery of quantum mechanics, for instance, revealed a subatomic world that defies classical intuition. Future theoretical breakthroughs, perhaps a successful theory of quantum gravity that unites general relativity with the quantum realm, could reveal new possibilities. It might suggest mechanisms for stabilizing such phenomena or ways to shield matter from the destructive plasma environment. The value of studying X-point portals isn't necessarily in their immediate utility as stargates, but in what they teach us about the fundamental processes of magnetic reconnection and energy dynamics. This knowledge is a crucial stepping stone. By mastering the physics of these natural magnetic phenomena in our own backyard, we build the foundational understanding that might one day, centuries from now, inform the technologies needed to manipulate space-time itself. For now, these portals remain incredible natural laboratories, revealing the universe's raw power and reminding us that the greatest discoveries often lie not in finding easy answers, but in learning how to ask better questions. And while these portals may seem like a unique feature of Earth's local space environment, they are actually a window into a process that is fundamental to the entire cosmos. The magnetic reconnection that creates X-point portals around our planet is not a local quirk. It is a universal mechanism, a fundamental way the universe transfers energy wherever magnetic fields and plasma exist. Our planet simply provides us with a convenient, nearby laboratory to study a phenomenon that is shaping events across the galaxy and beyond. Consider our own sun, for instance. The most violent eruptions in our solar system are direct cousins to the events we observe in Earth's magnetosphere, just on a vastly more powerful scale. A solar flare, that sudden and intense flash of radiation, is essentially a massive magnetic reconnection event happening in the Sun's complex atmosphere. When the Sun's magnetic field lines become twisted and stressed, they can snap and reconnect with a force equivalent to millions of hydrogen bombs, accelerating particles to near light speed and heating the solar plasma to tens of millions of degrees. Similarly, a coronal mass ejection, which hurls 1 billion tons of magnetized plasma into space, is launched by a large-scale reconfiguration of the Sun's magnetic field through this same reconnection process. The forces at play are mind-bogglingly larger than those around Earth, but the underlying physics is identical. By understanding the micro-scale details of an X-point portal near our world, we gain crucial insights into the engines that drive solar storms, which in turn affect our technology and climate. This cosmic connection extends far beyond our solar system. Spacecraft visiting other worlds have found evidence of magnetic reconnection throughout our planetary neighborhood. Jupiter, with its immense magnetic field, experiences colossal versions of these events within its magnetosphere, contributing to the planet's intense radiation belts and spectacular auroras. Even at Mars, which lacks a global magnetic field, reconnection occurs where the solar wind interacts with localized pockets of ancient magnetic crust. And in the vast, seemingly empty spaces between the stars, in what is called the interstellar medium, clouds of tenuous plasma are also governed by these magnetic interactions. Reconnection is thought to play a key role in heating this diffuse gas and influencing the formation of new stars. Wherever we find magnetized plasma, whether it's wrapped around a planet, flowing from a star, or drifting in the galactic void, magnetic reconnection is there, acting as a universal catalyst for energy release. Perhaps the most extreme examples occur in the most energetic environments imaginable, the regions surrounding black holes and neutron stars. These incredibly dense objects are often surrounded by spinning disks of superheated gas known as accretion disks. The magnetic fields within these disks are unimaginably strong and chaotic, creating conditions ripe for explosive reconnection. Scientists believe that some of the most powerful flares observed from black holes, events that can briefly outshine entire galaxies, may be powered by magnetic reconnection events within their accretion disks. In these distant, violent theaters, the process is amplified to cosmic proportions, accelerating particles to energies that dwarf anything we can create on Earth. The study of X-point portals in our own backyard provides a foundational model, a set of physical principles that astrophysicists can scale up to begin to comprehend the breathtaking power unleashed in these distant realms. This perspective transforms our understanding of Earth's place in the universe. We are not merely observers of distant cosmic phenomena. We are living inside a natural laboratory where one of the universe's essential processes is constantly on display. The flickering X-point portals above our heads are a local, accessible version of the same physics that governs solar flares, shapes the environments of other planets, and even powers some of the most luminous events in the cosmos. By decoding the secrets of these natural stargates, we are not just learning about our own space environment. We are developing a universal key, a fundamental understanding of how magnetic forces sculpt the universe, from our quiet celestial neighborhood to the most energetic frontiers of existence. This constant, hidden activity in the magnetosphere has very real and immediate consequences for the technology we have placed in the line of fire. While the auroras are a beautiful side effect, the intense radiation unleashed within these portals presents a clear and present danger to the intricate electronic ecosystems orbiting our planet. Every satellite, from a small communications CubeSat to a multi-billion-dollar observatory, is essentially a sophisticated computer flying through a natural particle accelerator. When an X-point portal opens and floods a region of space with high-energy electrons and protons, it creates a hazardous environment that these machines were never designed to withstand. The threats to satellite operations are multifaceted and severe. One of the most common issues is what engineers call a single event upset. This occurs when a single high-energy particle from a portal-related surge smashes directly into a microchip, flipping a memory bit from a 0 to a 1 or vice versa. It's a digital stroke of lightning that can cause a satellite to momentarily glitch, reboot unexpectedly, or even issue incorrect commands. While often temporary, these upsets can lead to a loss of critical data or service interruptions for GPS, television broadcasts, and financial networks that rely on precise timing. More catastrophically, sustained radiation can cause permanent damage through a process known as cumulative dose. Over time, this bombardment degrades solar panels, reducing their ability to generate power, and damages sensitive optical sensors like those on weather or spy satellites, effectively blinding them. In the worst-case scenario, a massive electrical charge can build up on the satellite's surface, leading to an electrostatic discharge, a miniature lightning bolt right on the spacecraft that can fry its electronics completely, turning a vital piece of infrastructure into silent, orbiting space junk. For the men and women living and working in space, the danger is even more personal. Astronauts aboard the International Space Station, orbiting in low Earth orbit, are partially protected by Earth's magnetic field, which acts as a shield deflecting many of the most dangerous cosmic rays. However, the particles accelerated by X-point portals are already within that protective bubble. During a significant portal event, the radiation levels inside the station can spike dramatically. While the station's hull offers some shielding, astronauts are advised to move to more heavily shielded areas, like the Russian Zvezda service module, during strong solar storms driven by these reconnection events. The risk isn't just acute, it's cumulative. Every exposure adds to an astronaut's lifetime dose of radiation, increasing their long-term risk of developing cancer and other health issues. This challenge becomes exponentially greater for future deep space missions to the Moon or Mars. Outside the relative safety of Earth's magnetosphere, a crew would be entirely exposed to the full fury of a solar particle storm funneled through these portals. Without the protection of our planet's magnetic shield, a single, powerful event could deliver a radiation dose capable of causing acute radiation sickness, threatening the success of the mission and the lives of the crew. This isn't a hypothetical future problem. It is the primary biomedical challenge that must be solved before humans can become a true interplanetary species. This is precisely why the science of predicting these events has evolved from an academic curiosity into a critical operational discipline. Space weather forecasting centers around the world, like the NOAA Space Weather Prediction Center in the United States, now operate 24/7, monitoring the sun and the solar wind in real time. Their goal is to provide advance warning, much like a terrestrial hurricane center. By tracking coronal mass ejections and monitoring the direction of the interplanetary magnetic field, forecasters can predict periods of high probability for intense magnetic reconnection and portal formation. When a southward IMF is detected barreling towards Earth, alerts are issued. Satellite operators can then take defensive measures, such as putting their assets into a protective, safe mode, by shutting down non-essential systems and orienting them to minimize exposure. Airline pilots flying polar routes, which are at higher altitudes and latitudes where radiation exposure is greater, can be instructed to alter their flight paths to lower altitudes. For mission planners at NASA and other space agencies, these forecasts are indispensable for scheduling spacewalks, ensuring astronauts are not outside the station during a radiation spike, and for designing the radiation shielding for next-generation spacecraft. The study of X-point portals, therefore, is not just about understanding the universe. It is about actively building a safer, more resilient future for our technology and explorers in the high frontier. The incredible discoveries from missions like MMS have not closed the book on this mystery. They have instead opened an entirely new chapter, filled with even more profound questions and the blueprint for a new era of exploration. The next generation of spacecraft and research initiatives aims to move beyond simply confirming that portals exist and begin to unravel the intricate details of how they live, breathe, and interact. Scientists are already designing missions that will act as even more powerful microscopes, peering into the heart of these magnetic explosions with a resolution we can only dream of today. One of the most exciting directions involves deploying not just 4, but a whole fleet of satellites. Imagine a swarm of 20 or 30 smaller, more affordable probes working in concert, forming a dynamic and reconfigurable observatory. While MMS's tetrahedral formation is perfect for capturing a single, 3-dimensional snapshot of an event, a larger swarm could do something even more revolutionary. It could track the evolution of a portal in real time. This swarm could spread out to monitor a much larger volume of space, acting like an entire network of weather buoys deployed across the ocean, allowing scientists to see how a reconnection event ignites at one point and then propagates along the magnetospheric boundary. Some proposed concepts even envision satellites with different specialized roles, some equipped with wide-field instruments to monitor the big picture, while others carry ultra-high-resolution sensors to zoom in on the microphysics. This multi-scale approach is crucial because the fundamental secrets of magnetic reconnection are believed to be hidden in the complex interplay between large-scale forces and tiny, particle-level interactions. The unanswered questions that drive this research are as compelling as they are challenging. First, there is the puzzle of predictability. We know the general conditions that favor portal formation. A southward-pointing solar magnetic field is the primary key, but we still cannot say with certainty exactly when or precisely where the next one will open. It's like knowing that a region is prone to thunderstorms, but being unable to predict the exact street where the next lightning bolt will strike. Is there a specific trigger, a final straw that causes the fields to snap? Are there subtle ripples or waves in the solar wind that act as a catalyst, seeding the instability that leads to reconnection? Answering this would transform space weather forecasting from a general warning into a precise prediction, giving satellite operators and astronauts specific, actionable timelines. Then we have the mystery of the microscopic realm. The MMS mission has given us an unprecedented view, but the most critical physics, the actual moment when the magnetic field lines break, may be happening on scales smaller than the satellites can currently resolve. This is the domain of kinetic physics, where the behavior of individual electrons and ions dictates the overall outcome. What are the precise mechanisms that cause the magnetic field to suddenly lose its grip, allowing it to reconnect? How is energy partitioned between different types of particles in that explosive instant? Understanding this is akin to moving from watching a car crash in slow motion to understanding the exact metallurgical failure that occurred within the engine at the moment of impact. It's at this infinitesimally small scale that the true engine of the portal operates. Perhaps the most complex question of all involves the interaction of multiple portals. Our current models often study these events in isolation, but the reality is likely far more chaotic and interconnected. During a major geomagnetic storm, it's probable that not just one, but many portals open and close in rapid succession across the magnetosphere. Do these events influence each other? Can the energy released by one portal trigger the formation of another nearby, creating a chain reaction of magnetic reconnection? Visualize it as a series of dominoes falling across space, where the collapse of one magnetic structure sets off its neighbor. Understanding this systemic behavior is essential for building accurate global models of space weather, as the cumulative effect of many portals could be far greater than the sum of their individual parts. This field is advancing at a breathtaking pace, with each new dataset from MMS challenging old assumptions and revealing new layers of complexity. The frontier of knowledge is constantly shifting. The ultimate goal is to weave all these threads together, from the vast, solar-driven patterns down to the dance of individual electrons, into a complete and predictive theory of magnetic reconnection. Achieving this would not only solve a fundamental puzzle in plasma physics, but would also give humanity a powerful new ability to navigate and thrive in our space environment. We are on the cusp of not just observing these natural stargates, but truly understanding the cosmic laws that write them into the sky. Given the incredible nature of this science, it's no surprise that the topic of natural stargates has captured the public imagination, often leading to a swirl of myths and misconceptions that blur the line between fact and fantasy. It's crucial to separate the established physics from the more sensational claims, not to dismiss the wonder, but to ground our awe in the even more remarkable reality. One of the most common misunderstandings is the idea that these X-point portals are stable, permanent structures, akin to the iconic rings from science fiction. As we've seen, the truth is the exact opposite. These are not fixed gateways but fleeting explosions, lasting for minutes at most before the magnetic fields reconfigure and the portal vanishes. Their instability is a fundamental characteristic, not a flaw. They are bursts of energy, not engineered architecture. Another pervasive myth suggests that ancient civilizations might have possessed knowledge of or even used these portals. While it's a compelling narrative for stories, there is simply no archaeological or historical evidence to support it. The physics governing these phenomena operates on a scale and in a region of space tens of thousands of kilometers above the Earth that was entirely inaccessible and undetectable to any ancient society. Their understanding of the heavens, while often advanced in its own right, was based on visual observation. The invisible magnetic dance that creates X-point portals requires spacecraft and sensors far beyond ancient capabilities to even detect, let alone utilize. The true story is not about lost knowledge, but about the gradual, painstaking process of scientific discovery that has allowed us, only in the last few decades, to begin to perceive this hidden layer of our universe. Perhaps the most elaborate misconception involves the idea that governments are hiding advanced travel technology derived from these portals. This notion fundamentally misunderstands the nature of the phenomenon. X-point portals are not a technology, they are a natural and intensely hostile force. As we've discussed, sending a probe through one would be like trying to send a paper airplane through the heart of a volcanic eruption. The seething plasma and intense radiation would destroy any known material instantly. The energy required to somehow stabilize such a maelstrom or create a safe passage is, according to our current understanding of physics, beyond astronomical. The real government research is not focused on secret star travel, but on the critically important work of understanding space, whether to protect our existing technology, our satellites, power grids, and astronauts from the very real effects of these natural events. So, if we strip away the myths, what are we left with? The facts are, in their own way, more breathtaking. These are not mystical gateways, but fundamental plasma physics in action. They are natural, transient phenomena that play a crucial role in the transfer of energy from the Sun to the Earth. This process is not a secret. It is a vibrant and open field of scientific inquiry, with data from missions like MMS publicly available for researchers around the world to analyze. The fascination with the idea of stargates is understandable, but it should not eclipse the profound significance of what we are actually learning. These portals are teaching us about one of the universe's primary energy transfer mechanisms, a process that shapes the environment of our planet, creates the auroras, and operates from the surface of the Sun to the edges of black holes. That is a truth more interconnected and wondrous than any fiction. To truly grasp the frontier of this science, we must now venture into a realm where the rules themselves seem to bend, the quantum world. For decades, the study of magnetic reconnection and X-point portals has been the domain of classical plasma physics, governed by the large-scale laws of magnetohydrodynamics. But a provocative question is now emerging from the theoretical fringes. What if the ignition of these cosmic portals is influenced by the bizarre, probabilistic laws that govern the universe at the very smallest scales? This is not to say that portals are a quantum phenomenon, but rather that the boundary between the classical and quantum worlds may not be as distinct as we once believed, especially within the incredibly intense and constrained environment of an X-point. The challenge lies in scale. The realm of quantum mechanics deals with particles like electrons and protons, while the phenomena we observe in space span thousands of kilometers. Traditionally, physicists have used approximations to bridge this gap, treating the plasma as a continuous fluid. However, at the very heart of the reconnection process, in the infinitesimally thin layer where the magnetic field lines actually break, this fluid approximation may break down. Here, the behavior of individual particles could become paramount. One tantalizing hypothesis suggests that a quantum process known as tunneling could play a role in initiating reconnection. In simple terms, quantum tunneling is the ability of a particle to bypass an energy barrier that, according to classical physics, it shouldn't be able to cross. It's as if a ball could suddenly appear on the other side of a hill without ever having rolled over the top. In the context of an X-point, the hill is the magnetic barrier that keeps the opposing field lines separated. The theory proposes that electrons, behaving as probability waves rather than simple particles, could tunnel through this barrier, effectively creating a microscopic short circuit. that triggers the large-scale magnetic explosion we observe. Another fascinating area of speculation involves the concept of entanglement. This is the strange quantum connection where two particles can become linked, such that the state of one instantly influences the other, no matter the distance between them. While applying entanglement to the chaotic, hot plasma of a portal is highly speculative, some theorists wonder if it could influence how energy is distributed among particles during the reconnection event. Could entangled pairs of electrons born from the intense energy of the process lead to correlations in their motion that we don't yet understand? This is frontier thinking with no experimental evidence yet, but it highlights the growing recognition that to fully model these extreme environments, we may need a theory that seamlessly merges the large-scale world of gravity and magnetism with the small-scale world of quantum probability. This quest for a unified understanding points toward one of the biggest unsolved problems in all of physics: quantum gravity. We have two brilliantly successful but fundamentally incompatible theories. Einstein's general relativity masterfully describes the force of gravity and the large-scale structure of spacetime, while quantum mechanics perfectly predicts the behavior of particles and forces at the subatomic level. Yet they refuse to speak the same language. The center of a black hole and the first moments of the Big Bang are realms where both theories are needed but where they clash violently. The environment within an X-point portal, while less extreme than a singularity, is another place where powerful gravitational fields are absent, but where electromagnetic forces are so intense that quantum effects might become significant. Studying these portals could therefore provide a unique natural laboratory for testing approaches to a unified theory, offering clues that might help bridge the chasm between the cosmos of the very large and the cosmos of the very small. This blurring of boundaries opens up a fascinating new frontier. It suggests that the universe's operating manual might have chapters that we are only just beginning to leaf through. The next generation of research will not only involve bigger satellite swarms and more powerful supercomputers, but also increasingly sophisticated models that incorporate these quantum mechanical considerations. The goal is to create a full kinetic description of reconnection, one that accounts for the individual dance of every particle while also capturing the grand spectacle of the global magnetic explosion. It is a monumental challenge, but the potential reward is a fundamental shift in our comprehension of how energy, matter, and information are woven together throughout the cosmos. The flickering portals above our world may hold the key not just to understanding space weather, but to deciphering the deepest laws that orchestrate the universe itself. Yet, even if these gateways remain forever beyond our physical reach, their very existence resonates on a level far deeper than pure physics. They offer a profound cultural and philosophical lesson, reframing our relationship with the cosmos in a way that is both humbling and inspiring. For centuries, the dominant human narrative has been one of separation, our small, fragile world set against a cold, distant, and largely indifferent universe. But the discovery of X-point portals shatters that isolationist view. It reveals that our planet is not a solitary island adrift in a silent sea, but an active participant in a continuous, vibrant dialogue with our star. We are not merely observing the sun from a safe distance, we are intimately linked to it through an invisible, dynamic tapestry of magnetic forces. Every time a portal flickers into existence, it is a tangible expression of that connection, a celestial handshake between the Earth and the Sun that happens dozens of times each day, whether we are aware of it or not. This transforms our cosmic address from a lonely outpost to a bustling intersection, a place where the fundamental processes that shape the galaxy are constantly on display. This realization carries a powerful poetic weight. The same cosmic forces that paint the auroras over our poles are also at work around distant planets and stars. The engine that drives a solar flare is a scaled-up version of the process happening just beyond our atmosphere. This suggests a universe that is not just vast but coherent, operating on a set of elegant, universal principles. We are not separate from this grand machinery, we are embedded within it. Our local space environment becomes a microcosm of the cosmos, a classroom where we can learn the basic grammar of the universe's magnetic language. Understanding the physics of an X-point portal near Earth is like learning to read a single word, which then allows us to begin deciphering the entire cosmic story, from the gentle stellar winds of red dwarfs to the violent jets erupting from supermassive black holes. This knowledge fosters a sense of cosmic kinship, an awareness that the physical laws we uncover in our own backyard are the same ones that orchestrate the dance of galaxies. The pursuit of this understanding is a testament to humanity's boundless curiosity and technological ingenuity. The fact that we can even detect these ephemeral events is a staggering achievement. It required us to conceive of invisible forces, design spacecraft capable of measuring them with exquisite precision, and develop the mathematical frameworks to interpret the data. This endeavor pushes the very boundaries of what is possible, driving innovation in satellite technology, data processing, and theoretical physics. It is a perfect example of how the desire to answer a fundamental question about our universe catalyzes advances that ripple through our entire technological civilization. The quest to comprehend these natural stargates is therefore not a niche academic exercise. It is a fundamental expression of the human drive to explore, to understand our place in the grand scheme of things. It inspires the same awe that early navigators must have felt when charting unknown oceans, except our map is made of magnetic field lines and our vessel is a constellation of satellites. Ultimately, this journey brings with it a necessary and healthy dose of humility. Nature, in its raw, unengineered power, creates phenomena that dwarf our most ambitious fantasies. The flickering, violent beauty of an X-point portal is a creation of pure physics, a wonder that arises spontaneously from the interaction of fundamental forces. It requires no designer, no builder, it simply is. This stands in stark contrast to our science fiction dreams of clean, stable stargates. The universe's version is far more powerful, more chaotic, and for now, entirely beyond our ability to control or utilize. It reminds us that for all our intelligence and technological prowess, we are still beginners in a universe that has been performing these feats for billions of years. We are learning to appreciate the artistry, not yet to wield the brush. This humility is not a sign of defeat, but a precondition for true wisdom. It grounds our ambition in reality, encouraging a relationship with nature based on observation, respect, and a patient unraveling of its deepest mysteries, rather than an arrogant assumption of mastery. In the end, these natural stargates may never carry our ships to the stars, but they have already given us something perhaps more valuable, a clearer, more wondrous, and more interconnected vision of the cosmos we call home. Let's try to make sense of these invisible cosmic forces by picturing them in ways we encounter in everyday life. Think of the magnetic field lines surrounding our planet not as rigid structures, but as incredibly flexible, high-tension elastic bands. In the quiet moments, they simply bend and sway, holding their shape against the gentle pressure of the solar wind. But when the sun's magnetic field flips to a southward direction, it's like two people start pulling on opposite ends of two different rubber bands, forcing them to cross. The tension builds and builds until suddenly they can't hold any longer. They snap at the point where they're pressed together, but in that very same instant, the broken ends instantly find a new partner and reconnect. That violent snap and immediate reconnection is the heart of magnetic reconnection, and the X-point is the precise, cross-shaped nexus where it all happens. This isn't a gentle process, it's a sudden release of pent-up energy, like a stretched rubber band finally giving way. Now, what happens when that cosmic snap occurs? Imagine you're in a perfectly calm, sealed room, Outside, a powerful wind is blowing. For the most part, the walls and windows hold firm and you feel only a faint draft. But then, someone suddenly flings open a door. Instantly, the calm inside is shattered as a tremendous gust rushes through the opening, scattering papers and whipping through the space. This is a powerful analogy for what an X-point portal does. Earth's magnetosphere is the sealed room, protecting us from the constant gale of the solar wind. The moment magnetic reconnection occurs and a portal opens, it's exactly like flinging that door wide open. It creates a direct temporary breach, and the solar wind, which was once flowing smoothly around our planet, suddenly has an invitation to surge directly inside, transferring massive amounts of energy and particles into regions that are normally shielded. As for the incredible particle acceleration that happens within these portals, we can think of it in two ways. The first is as a cosmic short circuit. In an electrical system, a short circuit occurs when current finds a new, unintended path of very low resistance, causing a sudden, massive, and often dangerous surge of power. An X-point portal acts in a similar way on a magnetic scale. The normal, more resistant path for magnetic energy is bypassed in the moment of reconnection, creating a temporary low-resistance pathway. This allows the vast stores of magnetic energy to discharge in an explosive surge, accelerating any particles caught in the flow to incredible speeds. It's an uncontrolled, violent release of power. The second, and perhaps more dynamic, analogy is that of a magnetic slingshot. Picture the magnetic field lines not as static bands, but as taut, invisible wires. When reconnection happens, these wires suddenly reconfigure, snapping into a new shape with tremendous force. Particles, like electrons, are like marbles sitting on these wires. When the wires snap and reform, the marbles are catapulted along them, gaining immense speed as they're flung outward. This slingshot effect is what hurls electrons down toward Earth's poles to create the aurora, and it's also what can fire them off into deeper space. It's a natural, incredibly efficient accelerator that takes tiny particles and gives them a kick of energy that our most powerful human-made machines struggle to match. These analogies, from snapping rubber bands to cosmic slingshots, give us a tangible way to grasp the powerful, invisible forces that are constantly reshaping the space around our world. Given the immense technological forces at play, it's only natural to wonder why we should invest significant resources in studying something so transient and seemingly abstract. The answer, however, lies not in the stars, but squarely in the security and stability of our modern, technology-dependent world. Understanding X-point portals is not a luxury of pure science. It is a critical form of planetary defense for the digital age. Every time one of these portals opens, it funnels the sun's raw power directly into the region of space where we have placed thousands of satellites that form the backbone of our global civilization. These assets, worth hundreds of billions of dollars, provide everything from global communications and financial transaction timing to weather forecasting, navigation, and national security surveillance. They are, in effect, the central nervous system of our modern economy. The violent particle radiation unleashed within these portals can degrade solar panels, cause crippling electronic glitches, or even permanently disable these vital machines. By learning to predict when and where these portals will form, we gain the ability to issue actionable warnings. Satellite operators can then put their valuable assets into a protective safe mode, temporarily shutting down sensitive systems to weather the storm, much like battening down the hatches before a hurricane. This predictive capability transforms a potential multi-million-dollar loss into a manageable operational procedure, safeguarding the infrastructure that powers our daily lives. This protective imperative extends far beyond orbit, right down to the power lines and pipelines crisscrossing our planet. During intense geomagnetic storms driven by successive portal openings, Earth's own magnetic field fluctuates wildly. These fluctuations induce powerful electrical currents in the ground, which seek the path of least resistance, often finding it in our continent-spanning electrical grids. These geomagnetically induced currents can overload transformers, the massive and expensive heart of any power system, causing them to heat up and fail. A widespread, cascading blackout triggered by a severe space weather event is not science fiction. It is a recognized risk that keeps grid operators and government agencies awake at night. The famous Carrington event of 1859 caused telegraph systems to fail and operators to receive shocks from their equipment. A storm of that magnitude today could incapacitate grids for weeks or months, with economic impacts running into the trillions of dollars. Research into X-point portals provides the foundational science needed to improve our space weather forecasting models, from a general warning of solar activity to a precise prediction of its terrestrial impact. This allows utility companies to implement protective measures, such as temporarily reducing load or installing blocking devices, effectively insulating the grid from the sun's fury. The return on investment for this fundamental research is measured in preventing catastrophic economic collapse. On a strategic level, accurate space weather prediction is becoming a new frontier for national and economic security, akin to dominance in cyberspace or on the high seas. For any nation or company with assets in orbit, superior forecasting is a decisive advantage. It allows for more resilient satellite operations, ensuring continuous service for military communications, intelligence gathering, and precision navigation. Airlines relying on polar routes, which expose passengers and aircraft to higher radiation levels during solar storms, depend on accurate forecasts to reroute flights for safety. The Global Positioning System, or GPS, which has become essential for everything from banking to transportation, is highly vulnerable to disruptions in the ionosphere caused by energy dumped through these portals. A nation or company that can better predict and mitigate these disruptions gains a significant edge in reliability and operational continuity. This is why space agencies and defense departments around the world are major funders of this research. It is no longer just about understanding the universe, but about maintaining a strategic advantage in an increasingly contested domain. Framing this work as merely basic research sells short its profound practical value. It is more accurately described as a pre-competitive investment in global technological resilience. The knowledge gained about plasma physics and magnetic reconnection doesn't just help us predict space weather. It advances our fundamental understanding of how to manage plasma here on Earth, with potential applications in developing fusion energy. It drives innovation in satellite design, leading to more radiation-hardened components. It pushes the limits of high-performance computing as we create ever more sophisticated models. By investing in the curiosity-driven quest to understand a mysterious phenomenon in near-Earth space, we are simultaneously building the scientific and engineering capacity to solve some of our most pressing technological challenges. The economic and strategic case is clear. Funding the study of X-point portals is not an abstract academic exercise. It is an essential investment in protecting the technological foundation of 21st century society, ensuring that as we reach further into the cosmos, we also learn to safeguard the world we call home. What's truly remarkable about this field of research is that you don't need a PhD or access to a multi-million-dollar spacecraft to be a part of the discovery process. The quest to understand these natural stargates is in many ways a collective human effort, and there are powerful ways for anyone with curiosity and an internet connection to contribute directly. This is the world of citizen science, where public observations become valuable data points that help professional researchers piece together the larger cosmic puzzle. When you step outside on a clear night and look up at the aurora, you are witnessing the final, beautiful step of a process that began at an X-point portal hundreds of thousands of kilometers away. That observation is more than just a spectacle. It can be a crucial piece of scientific evidence, organizations like the Auroras project have built entire platforms around this idea. This is a citizen science initiative run in collaboration with NASA and the National Science Foundation that allows anyone who sees the northern or southern lights to report their sighting through a website or a mobile app. Why is this so valuable? While satellites like MMS can measure the reconnection event happening in space and other spacecraft can observe the aurora from above, the view from the ground provides a unique and irreplaceable perspective. Amateur astronomers and casual sky watchers report the color, intensity, structure, and location of the auroral display. When these thousands of individual reports are aggregated, they create a high-resolution, real-time map of the aurora's extent and activity. Scientists can then correlate this ground truth data with the satellite measurements taken at the same time. For instance, a report of a sudden, dramatic brightening and southward surge of the aurora from observers in the northern United States can be directly linked to a specific, powerful reconnection event detected by the MMS mission in the magnetosphere just minutes before. This partnership between eyes on the ground and eyes in space creates a much more complete picture of how energy from these portals travels and manifests around our planet. Beyond just watching the sky, you can also access the very same data streams that scientists use. NASA and the National Oceanic and Atmospheric Administration, or NOAA, make near real-time data from their fleet of solar and space weather satellites publicly available online. Websites like the NOAA Space Weather Prediction Center or NAS, a space weather media viewer display live information on solar wind speed, the direction of the interplanetary magnetic field, and geomagnetic activity levels. This means you can literally watch as a surge in the solar wind approaches Earth, see the magnetic field orientation flip to the south, and then, by checking the aurora forecast or looking outside if you're at a high latitude, witness the potential consequences. Engaging with this data transforms an abstract concept into a tangible, observable phenomenon. You can start to see the patterns for yourself, developing an intuitive understanding of the cause and effect relationship between the sun's activity and the resulting space weather around Earth. It demystifies the science and empowers you to become an informed observer of our dynamic space environment. To stay connected to the cutting edge of the research, you can follow the missions themselves on social media. The magnetospheric multiscale mission, for example, has active accounts on platforms like X, formerly known as Twitter, and Facebook, where the team posts updates, stunning visualizations from their data, and alerts about significant solar events. NASA broader public outreach websites such as NASA Science offer a treasure trove of articles, podcasts, and image galleries that break down complex findings into accessible and engaging content. By following these channels, you become part of a global community of enthusiasts, students, and professionals who share a fascination with the invisible magnetic forces that shape our world. This sense of shared discovery is a powerful thing. It fosters a connection not just to the science but to the human endeavor of exploration. You are no longer a passive spectator but an active participant in a grand, ongoing investigation to understand our place in the cosmos, a journey that is rewriting our understanding of the sky above and revealing the hidden architecture of the universe we inhabit. But the story of these magnetic portals does not end at Earth. In fact, our planet is just one example in a vast cosmic family, each member offering a unique laboratory to observe how these fundamental processes play out under different conditions. This comparative approach, looking at other worlds in our solar system, reveals a stunning diversity of magnetic personalities and shows us that the phenomena we see here are universal, just amplified or diminished by local circumstances. Consider Mars, our neighboring planet, and a stark contrast to Earth. Mars presents a cautionary tale of what happens when a world loses its global magnetic shield. Billions of years ago, Mars likely had a much stronger magnetic field, generated by a churning molten core, much like Earth's does today. but as the planet's interior cooled, that dynamo shut down, leaving only faint, fossilized magnetic fields locked in its ancient crust. Without a strong, global magnetosphere to deflect the solar wind, Mars is exposed to the full brunt of the Sun's fury. The solar wind doesn't encounter a unified magnetic barrier. Instead, it strikes the Martian atmosphere directly. This doesn't mean magnetic reconnection is absent. In fact, it occurs in a more patchy and complex way. Wherever a remnant crustal magnetic field exists, it can interact with the carried magnetic field of the solar wind, creating miniature, localized versions of X-point portals. These events are not as globally significant as Earth's, but they still contribute to the slow, relentless stripping away of the Martian atmosphere by the solar wind. Studying Mars gives us a sobering view of a world where the protective magnetic handshake with the Sun has been severely weakened, and it highlights just how crucial our own magnetosphere is in preserving the conditions for life. On the opposite end of the spectrum lies Jupiter, the solar system's gas giant and a magnetic powerhouse. Jupiter's magnetic field is an absolute behemoth, generated by a vast interior of metallic hydrogen. If you could see Jupiter's magnetosphere from Earth, it would appear larger than the full moon in our sky, even though it's over 400 million miles away. Within this colossal magnetic bubble, everything is amplified to an almost incomprehensible scale. The volcanic moon Io, spewing tons of material into space, constantly feeds Jupiter's magnetosphere with fresh plasma, creating a donut-shaped cloud of charged particles that spirals around the planet. This sets the stage for magnetic reconnection, events that dwarf anything we experience at Earth. The energy releases are so titanic that they create Jupiter's immense and permanent radiation belts, regions so intense they pose a lethal threat to any spacecraft that ventures too close. The auroras at Jupiter's poles are not fleeting, delicate curtains of light. They are permanent, continent-sized hurricanes of energy, hundreds of times more powerful than Earth's, glowing in ultraviolet and X-ray light. They are fueled by a constant, dynamic interplay of magnetic forces, including powerful reconnection events in Jupiter's own magnetotail. Jupiter shows us what happens when the ingredients for portal formation, a strong magnetic field and a plentiful supply of plasma, are turned up to their maximum setting. Even worlds without any global magnetic field of their own can teach us valuable lessons. Venus, for example, is similar in size to Earth but has a very weak magnetic field. Its interaction with the solar wind is different yet again. Instead of being deflected by a magnetic shield, the solar wind slams directly into Venus's thick, ionized upper atmosphere known as the ionosphere. This creates a different kind of boundary where the pressure of the solar wind compresses the ionosphere itself into a protective, comet-like shape. Magnetic reconnection can still occur as the solar wind's magnetic field drapes around this obstacle and eventually reconnects in the long tail that stretches away from the Sun. Studying Venus helps us understand how an atmosphere alone, without a planetary magnetic field, can act as a buffer against stellar winds, a critical consideration when searching for habitable planets around other stars. This grand tour of our solar system underscores a profound point. The physics of magnetic reconnection and the formation of these X-point portals is a universal language. The same fundamental equations describe the explosive energy release at Earth, the patchy interactions at Mars, and the colossal storms at Jupiter. The differences we observe are not due to different laws of physics, but to different local conditions, the strength of the magnetic field, the presence or absence of an atmosphere, and the availability of plasma. This makes our solar system a perfect natural laboratory. By comparing these worlds, we can run a controlled experiment, seeing how one variable, like magnetic field strength, changes the entire system's behavior. Earth, with its moderate field and protective atmosphere, offers a stable and observable case. Mars shows us a world in decline, Jupiter a system of overwhelming power, and Venus a study in atmospheric resilience. Together, they provide a complete picture of the many ways a planet can interact with its star, revealing that the invisible magnetic dance we are only beginning to understand at home is a symphony playing on a galactic scale. So let's step back and take in the full, breathtaking panorama this science reveals. We are not living on a solitary rock drifting in a silent, empty void. Instead, our entire solar system is a vast, dynamic, and deeply interconnected physical engine, with the Sun as its brilliant, beating heart. From its turbulent surface, our star perpetually exhales the solar wind, a supersonic river of energy and particles that flows outward, bathing every planet, comet, and asteroid in its influence. This wind is the Sun's extended presence, carrying its magnetic fingerprint to the furthest reaches of its domain. It is the primary force that shapes the environment of every world it touches, a constant cosmic weather system that is anything but placid. Within this flowing stellar atmosphere, each planet responds in its own unique way, creating a fascinating family portrait of celestial interactions. Earth's response is particularly elegant. Our planet's global magnetic field generates a protective shield, the magnetosphere, which acts like a sophisticated deflector. It doesn't simply block the solar wind, it engages with it. The magnetosphere sculpts the incoming flow, channeling it around our world in a complex, ever-changing dance. But this shield is not an impenetrable wall. It is a dynamic and permeable boundary, and the X-point portals are the crucial pressure release valves in this system. They are the temporary openings that allow for a controlled yet explosive transfer of energy. This isn't a flaw in the design. It is the essential mechanism that allows our planet to manage the Sun's constant output. The entire system operates in a state of dynamic equilibrium, a continuous push and pull between the inward pressure of the solar wind and the outward resilience of our magnetic field, with portals serving as the momentary bridges that keep the entire structure from becoming overly stressed. This grand interplay transforms our perception of Earth's place in the cosmos. We are not merely observers of the Sun from a safe distance. We are active participants living deep inside the Sun's extended atmosphere. The space between the Sun and Earth is not empty. It is a seething, structured medium of magnetic fields and energized particles. Every minute of every day as you go about your life, this invisible dance is happening all around you. Dozens of times a day, vast magnetic portals flicker into existence tens of thousands of kilometers overhead, transferring immense amounts of energy that will eventually paint the polar skies with light or stir up the radiation belts that surround us. Our planet is not a closed system. It is an open one, intimately linked to our star through these cosmic circuits. This holistic view reveals a solar system that is vibrant, active, and unified by fundamental physical processes. The same magnetic reconnection that creates an X-point near Earth is also igniting solar flares on the Sun, contributing to the intense radiation belts around Jupiter and influencing the thin atmosphere of Mars. We are seeing different expressions of the same universal laws. By studying our own local space environment with such exquisite detail, we are effectively learning the basic grammar of a language that is spoken throughout the galaxy. It allows us to look at a distant star and with growing confidence begin to imagine the complex magnetic interactions that might be occurring around any planets in its habitable zone. Understanding that we live within a giant, active physical system, one that is constantly interacting and evolving, is the final and most profound lesson of the X-point portals. They are not just curiosities, they are our local tutors, teaching us that the universe is a place of continuous connection, where nothing, not even the space between worlds, is truly still. So as we reach the end of our journey, let's gather the most important threads. The central, undeniable fact is this: X-point portals are real. They are not science fiction, but a confirmed natural phenomenon occurring dozens of times each day in the space around our planet. They are born from the explosive process of magnetic reconnection, a fundamental cosmic engine where the magnetic fields of the Sun and Earth collide, break, and reconnect in a violent release of energy. These are not the stable, glowing rings of cinema. They are vast, fleeting, and intensely powerful maelstroms of plasma, acting as temporary bridges in the invisible magnetic architecture that envelops our world. The significance of these portals extends far beyond their existence as a scientific curiosity. They are the primary drivers of space weather, acting as cosmic gatekeepers that control the flow of solar energy into Earth's environment. When they open, they funnel the Sun's power directly into our magnetosphere, with consequences that are both beautiful and formidable. They are the invisible artists behind the auroras, painting the polar skies with light by accelerating particles down our planet's magnetic field lines. Yet, this same process can trigger geomagnetic storms powerful enough to disrupt satellites, threaten power grids, and challenge our ambitions for human spaceflight. Understanding them is not just an academic pursuit. It is a critical step toward securing our technological future and safely navigating the high frontier. While they may not be the traversable stargates of our dreams, what they represent is, in many ways, more profound. Their existence reveals a universe that is deeply interconnected and dynamically energetic. Our planet is not an isolated island in a quiet void, but an active participant in a continuous, vibrant dialogue with our star. The flickering of these portals is a constant reminder that we live within the Sun's extended atmosphere, connected by invisible magnetic threads. This knowledge transforms our cosmic perspective, replacing a sense of isolation with one of belonging to a vast physical system. The adventure is far from over. With missions like MMS and the next generation of satellite swarms on the horizon, we are only just beginning to decipher the full complexity of these phenomena. Researchers are pushing into new frontiers, exploring the potential links to quantum physics and refining models that will one day allow us to predict space weather with the same reliability as terrestrial forecasts. Every new dataset peels back another layer, revealing a universe that is more intricate and wondrous than we imagined. The greatest takeaway is an invitation to see the sky with new eyes. The next time you gaze up at the stars or are lucky enough to witness the shimmering dance of an aurora, remember the hidden reality. In the darkness above, an immense invisible drama is continuously unfolding. Vast magnetic forces are writhing, and temporary doorways are flickering into existence, connecting our world to the cosmos in a fundamental and breathtaking way. This ongoing discovery reminds us that the universe is filled with wonders not just in the distant galaxies, but right here, in the space embracing our fragile world. Stay curious, for the story of our connection to the stars is being rewritten above our heads every